Yeah, thanks, Federica, and thanks everyone for joining. You see, even a couple of people from my time zone. It's 7 a.m. here, so special welcome to everyone who woke up early. I'm Mario Juric. As Federica said, I'm the director of the DiRAC Institute at the University of Washington and astronomy faculty at UW. I will tell you about the JupyterHub we rolled out as a part of LINCC to basically help people start working on preparatory science with LSST, enable collaboration, and just make it easier for all of us to be ready in about 2 years when LSST starts delivering data. So before I start, let me just introduce my collaborators and co-authors here, and colleagues and students who have done the vast majority of the work that I'm going to show you here. Steven Stuckler, especially one of our grad students at the astronomy department, he's been instrumental in putting together this hub and all the systems behind it. Colin Slater is working on distributed data processing. And then our team of support, our supports team, Aditi, Aidan, and Paolo, who are current or former undergraduates at UW, who will be supporting you if you have a question on Slack, or if you request any package to be installed or something like that. They're probably the ones who are actually going to do it. So all credit goes to them for things that work. Let's start by talking about, let's begin with talking about LINCC first. What is LINCC? It stands for LSST Interdisciplinary Network for Collaboration in Computing, and it's an initiative of LSST Corporation aiming to help the LSST user community, that means us, to prepare for LSST science. And this is quite a broad initiative. There are three key goals here. One is to open discovery space to a larger and more inclusive community. How do we make it easy to folks who have not been intimately involved with LSST development over the last 15 years to actually start using all the software and data that we're producing for LSST, to foster creation and sharing of analysis tools and data for key LSST science goals. There's much software to be written to be ready on day one. We want that software to actually be written and then shared among the community. And three, to train and mentor really the future scientific leaders. There's a lot of knowledge here that's not typical to astronomy. How you deal with petabyte-sized data set, or not typical to every single astronomer. How to deal with petabyte-sized data sets. How do you analyze billions of observations in a statistically correct manner? So there'll be things like fellowships and LINCC hubs, centers of excellence, basically, where we will be trying to make sure to make that knowledge available to the community, and to have people who will then be postdocs at LSST's institutions, at these hubs, and then go out in the community and help spread that knowledge as well. For this goal, for this session, I'm mostly focused on this first part. So opening discovery space to a larger, more inclusive community. There are many ways how this will be done and can be done, but one really simple one, which we started, was to set up a central JupyterHub, a central location where anyone in this group, anyone who's a member of these science collaborations can go. They can easily try running LSST data analysis code. They can access LSST simulations. They can get some CPU cycles. They can collaborate within their group, and they can collaborate together as a whole collaboration on LSST science. LINCC, as I mentioned in the previous slide, is something that just launched. We quite literally have 0 staff at the moment. All the hiring is happening, but much more is to come in 2022. However, this JupyterHub that I'm going to show you is something that we at UW's DiRAC have set up about a year ago for the LSST Solar System Science Collaboration for this purpose. It was very useful, and then when this Heising-Simons proposal was accepted, we decided to expand it out to everyone, even before the LINCC proper kind of started up. So the reason why I mentioned that is you will soon see There are many things that talk about the solar system in these slides, and you'll see on the hub itself there are a few solar system things that are installed. That's why. That's the history of these resources. So, what is this that I'm going to talk about in this hub that I'm going to talk about in one slide? It's basically a setup of Jupyter on cloud resources. As I mentioned, it started as a platform for LSST Solar Science Collaboration sprints. Now we're expanded it to TVS and Milky Way collaborations. Actually, honestly, anyone in all collaborations is welcome, but we're really focusing on these three because of the HSF support. Uses well-known Jupyter interface. It allows you to access a choice of different nodes on AWS. Allows you to, for example, spin up GPU nodes if you need to do some training or some analysis that requires GPU code. Has a shared file system. Has pre-installed LSST DM stack simulations, DM and software and simulation software stack. Has a number of science-specific data sets. For example, we have a simulated solar system data set on the hub already pre-installed. Comes with a Jupyter Lab environment and also comes with a virtual desktop environment, so you can actually run graphical applications on it. And over the next hour or so, I'm going to walk you through all of this. The idea is to make sure that you're able to log in, that you know what features are available, and that you know how to collaborate, and that you hopefully start using this either for collaboration within your science collaboration or even within your group. For example, this hub is something that we at UW use regularly, even for just internal work by our groups. So this is kind of the program, what to expect. I'll start with making sure that we can all log in. So we'll talk about how to access the Jupyter Hub and make sure that everyone has accounts. Then I'll give you a very short introduction to Jupyter. To those of you who are new, I'll talk about the available software. I'll show you how to install your own software, both with Conda and if you need to build it. I'll talk about features for collaborations. The big point of this hub is to make collaborating really, really simple. Let's talk about how to manage the collaboration software that you would you install and share for a collaboration. Then I'll talk a little bit about available resources, so memory, CPUs, GPUs, remote desktop, and then I'll finish with talking about where to get support, who to go and talk to, and where, and some future plans. And then the idea is to leave a lot of time at the end for just discussions and questions and troubleshooting. Okay, if you have questions at any point, please do raise your hand on Zoom, and then or ask a question in Slack. I prefer here, actually, if you raise your hand, I can see you the way I have things set up. If you ask a question in Slack, then that will alert me to it. But in any case, don't wait if something's not working for you. Don't wait until the end. Ask a question, and we'll try to debug it so that you can follow along.
Mario, we have a lot of Slack channels, right? So just to clarify, is there a specific channel that you want people to submit questions to?
Yeah, perfect segue into this slide. Go to, I just opened a new channel yesterday specific for this hub on the LSSTC Slack. So that's basically the only requirement to join the hub, to have an account on the LSSTC Slack. Go to LSSTC Slack and join LINCC Hub. So LINCC Hub channel, let me see. I'm going to go.
I think I can post the link to the channel in a few seconds.
That if you can post a link to the HSF channel and anywhere else where might be useful. Yeah, I see people trickling in. I see you, Federica. There's Krista, Alessandro. Okay, so as you're coming into that channel, here I lied. It's not just the LSSTC Slack. You'll need two things. One is a GitHub account, and I suspect most of you have it. If you don't, go to github.com and open it. It's free and available to everyone. And then the second thing, once you have a GitHub account, is you'll need a membership in the LINCC Hub GitHub organization, or in one of the GitHub organizations of your science collaborations. So if you're a member of the Milky Way Science Collaboration, I think it's Ruben-MW. If you're a member of TVS, then it'll be LSST TVS-SC, and if you're a member of Solar System, then it's, I think, LSST SSSC. If you have any doubts about whether you're members of those or not, then we'll make you members of the LINCC Hub organization. How to become a member? Join that channel that I just mentioned, and just post your GitHub username there, and then our admins, or in this case Federica, will just add you, will invite you to the organization. So just drop a short message, or just even drop just your GitHub username. That's the only thing we need to know. What's your GitHub username, so we can send you this invitation. So I'm going to pause here for a couple of minutes and let you actually start sending those usernames, and I'm going to go and Federica and I will start adding you. Just one note, as this is ongoing, once you get invited, you're going to get an email, but you'll also be able to go just to this link for the organization. You'll see a banner on top saying you have been invited to this organization. You must accept that invitation for any of the rest will work. So that's the first thing to mention. And I'll paste this link. Here we go. So this link that I just sent will take you to the organization. The second thing is, once you get invited and accept membership in the organization, please do not log into the hub quite yet. So after you do it, I want to show you a couple of things before you do the first login, and it'll be easier if you haven't logged in yet. All right. So as I mentioned, the first step was to make sure to accept an invitation to join. Apologies for the typo. To join LINCC-Hub LINCC Hub on GitHub. The second step, once you've done that, is to go to lsst.dirac.dev. You're going to see some things being named LINCC and some things being named DiRAC. This is a reflection of that history, that this started as a project of ours at UW's DiRAC Institute, and now we're folding it into LINCC. So not everything has been migrated yet, but all of these links will continue to work indefinitely. So if you learn one and get used to one, don't worry about having to change your habits later. So go to lsst.dirac.dev, and what you should see there is a screen like this. So this here is the sign-in form for GitHub. Sorry, for the LINCC Hub. If click on sign in with GitHub, and the first time you sign in, you're going to get, assuming you're logged into GitHub. If you're not logged into GitHub, it'll ask you for your GitHub user account details and login. If you are logged into GitHub, it will give you this kind of screen the first time you sign in. So this bit is important, and I wanted to explicitly show it. These here are all the organizations that you're a member of. Everyone will have different set of organizations. These are mine. And the little check mark next to each organization are organizations to which LINCC JupyterHub will have access to. It'll be able to know that you're a member of those organizations. You're going to see that there are some that it'll know about by default, and then there are some that where you may need to grant it permissions to for it to know about those organizations. And there's some where you're not an administrator, so you have to request permission for the LINCC Hub to be given access to them. Any organization that you're going to with whose people you're going to collaborate. Let's say I'm a member of the Deep Survey, and we're likely to use this hub to do some data analysis. So I want to make sure that the hub knows about the Deep Survey collaboration. Click Grant on any such collaboration. So I'm going to do that for SIMA as well. And let's see, for Astor Institute colleagues. This is why I didn't want you to log in right away, because I wanted to point this out to you. This is the part that if you don't get this done, there's a way to do it later, but it's actually a bit more complicated if you realize that an organization is missing that you want to be a member of. Okay, so after you've selected the organizations that you want JupyterHub to know about, click Authorize Astronomy Commons. And then what should happen is you should find yourself back on lsst.dirac.dev at a screen that looks like this. So for now, just go ahead and click Start. And when you click Start, what should happen is the hub will activate, and it will start up a Jupyter Notebook server for your use. This step is something that we're working on improving. Right now, it takes between 2 and sometimes up to 5 minutes to actually get you to a point where you can work in Jupyter. This is only the first time that you log in. Once you log in, it'll actually work quite smoothly. But this is the kind of thing where improvements are on the way and possible to just make this faster, so that in about, we're aiming for about 30 seconds or so for this startup. What's happening in the background is now JupyterHub knows who we are, and it's talking to Amazon Web Services to actually get you a virtual machine that you're going to be using, that you're going to be working on, and start Jupyter there and log you in. So if you've successfully logged in, this is likely what you're going to see. So just with just one folder named link and everything else empty. If you've used the hub before for Solar System Science Collaboration sprints, you're probably going to see more files in here, but if this is the first time you're using it, this is all that you're going to have. This is just a classic Jupyter interface. So anything that you're used to doing in Jupyter, you can do here. You can navigate directories, you can create files, you can create notebooks, all of that works. If you are a fan of JupyterLab, that's a different interface for Jupyter. The way to switch to JupyterLab is in the address. You're going to see that there's lsst.dirac.dev/user/your username/tree. Just change that tree to lab and hit enter. So for example, instead of tree, I'm going to put lab, hit enter. And then after a little bit of waiting for everything to load, I'll be given a JupyterLab interface. And so if you know how to use JupyterLab, this is just JupyterLab interface, and you'll be right at home. I kind of prefer this classic interface, so most of this demo is going to be in the classic interface. And let me zoom in a little bit so that you can see this better. So JupyterLab is installed, although it's not there by default. Another thing that JupyterHub gives you is terminal. So this is something that we don't typically use when we run Jupyter on our desktops, because we can just open a full-blown terminal application. But when running Jupyter on a remote resource, this becomes very handy and useful. So if you click New and then Terminal, it will open in another tab a full-blown terminal emulation. So this is, on the other hand, this is like as if you were SSH into a machine. You can do LS, you can ask how much disk space is available. You can run top to see who's running. You're going to find out that you're the only person on the machine. etc. This is great for doing things like downloading data sets, organizing directories, moving things around, and we'll see in a bit also for using software. So if you've never used this, the terminal emulation in Jupyter, this is something that I would really wanted to introduce to you. Okay. Let me move on. So what is this? I mentioned already what basically just happened here while we were logging in. When you logged in and clicked start, that big orange button at the beginning, Jupyter asked Amazon Web Services, so AWS, to give you a dedicated machine for your own use. There's an asterisk here because for those of you in to know, it's not really a machine, it's a container, but it feels like just your own personal virtual machine. This virtual machine, this machine that you've been given, is yours. So you're the only person on it. Every person gets a different one, so you don't clash with others' work. It also means that if it says that it has 16 gigabytes of memory or 128 gigabytes of memory, those are all your gigabytes of memory. It doesn't depend on how many other people are using the system at the same time. Everybody gets their own machine. The one thing that those machines share is a common file system. So the directories with software and files, the home directories, they are visible from all these machines. This is very much similar to how office computers in many institutions are used and how they see the same file system. The difference is that here, this machine can only be accessed through Jupyter, so through the notebook, through the Jupyter Lab or terminal. That's especially why I'm showing the terminal. And we'll be adding more ways to access these machines. Like one is going to be direct SSH access. That's in the works, probably next week that's going to land. We'll eventually add a possibility to mount the drive as a shared network drive directly on your MacBook or on your Linux machine or on your Windows machine even, to just drag and drop files across. So that should be pretty useful. And the important thing here is that in these cloud-based Jupyter installations, it does look at whether you're using it or not. And if you're not, it'll shut down the machine to conserve resources. So if you're not using Jupyter for more than an hour, which doesn't mean that you didn't click on it more than an hour. It basically means that you've closed these windows where JupyterHub is open for longer than an hour. It will detect that as inactivity and it will shut down the machine. So to conserve resources, everything that's on disk, all the files that have been saved, all the Jupyter notebooks automatically get saved. All of those are going to be preserved, but you will have to restart the notebook next time you come online. That's the only detail with how that works. We actually have something in preparation to make that go away, to basically have these notebooks active throughout. But that really needs to await the LINCC software development team that we're currently in the process of hiring. Okay. All right. So I think most people are already familiar with how JupyterHubs work. Let's talk about what's available on this one. So if you click on the new button, you'll see a list of notebook kernels that are available to you. This list shows the solar system heritage of this hub a little bit. We have the first one, the Python 3 kernel, is the one that you should use if in doubt. So if you don't know which one to use, if you're not certain, just use the one that says Python 3. So what this kernel has is it comes with Python 3 installation and a reasonably current LSST stack release. So let me just show you that it works. So here's an example of just running something simple to test that this works. If you need an older version of the LSST stack, there's also one from 2020. This is the one that we ran for the Solar System Sprint back in 2020. This is the one from 2021. That's basically the difference. There's also Python 3 Sims kernel installed right now. What this comes with is a recent install of Rubin Sims tools, and these are tools for simulations. So I suspect that this is going to be widely used in this community. So let me switch to kernel. Well, actually, let me just show it to you here. So this allows you to use tools to use things like math. So if you're analyzing metrics, if you're developing metrics for cadence studies, this is the place to go and to have all that software pre-installed. So what I'm going to do now is I'll demo a little bit of how that works by running one of the math demo notebooks for you. So if you're logged in, here's what I'm going to ask you to do, and I'll paste these commands into Slack as well, so that you actually try it out. So if you open, if you're on the hub, open the terminal, and then type. Let me make this slightly smaller, and then type git clone, and then this address where the Rubin Sims notebooks are, and I copied the same command into the LINCC Slack channel, so you can just go ahead and copy and paste it from there. Okay. And I'm going to pause here just for a minute for those of you who are on. If you can give me a thumbs up on LINCC when you've done the clone, so I know that if I have a feeling how many people are following along. Mm-hmm. Okay. All right, I see thumbs up, or thumbs are going up. Good. So now let's see, let's go into one of those notebooks. Let's go into Rubin Sims notebooks, math, perhaps tutorial. And let's do the one that says survey footprint. And that one actually has a few figures. All right. So now it says kernel starting at my end. And so now what I'm going to do, I'm going to start this. And when I start it first, you'll notice that it'll throw me an error. And I just want to illustrate a point on this. So let me start executing. So this worked. And when I run the next command, it says module not found, Rubin Sims. Martin has a hand up. Do you have a question?
Sorry. Yes,
yeah.
I could git clone, but how could you get to this window?
Okay. So go back to where your Jupyter. If you cloned it in a terminal, your terminal is probably in a separate tab. So if you go back to the tab that has homepage, you should see it somewhere in there.
Okay.
Did that resolve it? Does that work?
Mario, the path to the notebook perhaps helps. So you go to Rubin Sims maths tutorials.
Mm-hmm, mm-hmm. Oh, yes.
And I posted that on Slack and chat.
Rubin Sims math tutorial, and then we'll pick the survey footprint one. Yeah. So let me go back to my survey footprint. When I started executing, if you start executing it, you'll notice that there's an error in box 2, and the reason for that is by default all these notebooks usually pick up the Python 3 kernel that they find in the system, and in our case, remember that I showed you that Python, the simulations are installed in this environment that has Python 3 sims. So what you'll need to do is you'll basically have to tell it to use the correct environment. So you go to kernel, change kernel, and then select Python 3 since 2021. And and I'll pause here so that to make sure that you see what where you need to go. So if you click on that, it'll restart. So again, kernel, change kernel, Python 3 since 2021. Now, if you re-execute these cells, now everything should work. And now cell number 2 worked. So I'm going to go and run this until I get to the first figure, just to show you that that things are happening. And this is a point where it's going to go ahead and calculate some metrics. I'm actually not sure what this one does, but it'll make a plot eventually. So let me ask you to follow along and also get all the way through here where it says bundle.plot, and then we're going to get this nice sky map by the time we get to column 10 or to cell number 10. This usually takes about a minute.
Mario, can you maybe go over the steps one more time? Martin, would that help? Oh, seems that's resolved.
All good? Okay. And so at this point, this is really, the system is doing work, and we're waiting, not because of something peculiar to Jupyter, but because it's just doing a lot of computation on 10 years of the survey. And here we go. So we ran through here. The rest requires some downloading, so I'm not going to go through that. If you do, then make sure to follow these instructions. But the point here was, if you're using this JupyterHub, you have all this pre-installed. So if you need to run some metrics, understand how a potential cadence change is going to affect your science, you can quickly get that notebook onto here, start it up, use the Sims kernel, and it'll just work. And as this LSST Sims team produces newer and newer versions of Sims tools, we'll just keep updating them regularly and keeping the old ones so that your old notebooks continue to run if you don't want to update them. So this is really the kind of thing that you get out of hubs like this. The ability to quickly get started and get to things like making plots like this and writing metrics without having to go through potentially a couple of hours of installing everything in your machine and debugging. Okay, so the other kernels that you're going to see here, there's one called LSST 2020. I already mentioned that one is that's an older version of the stack. Usually you never want to use older versions of the stack, but if you do have things that depend on them, we'll maintain them. One of the things that we're trying to do with this hub is make everything backwards compatible. If you start working on it, if you really invest your time into making this your home for collaboration, we'll make sure that things continue working even as LSST stack changes. If you don't want to upgrade that, you don't need to. And it was one that was a demo of MAST at the Solar System collaboration hack week a couple of months ago. More will start showing up here as more software is added to the hub. All right. So that's the software that's currently installed. As you can tell, it's just the most recent versions, and more will be added as we get more people on and as people start making requests. Now, let's talk about how we make this. I mean, it's great to have a platform with all the software pre-installed, but I think the real power in collaboration comes from being able to customize it, being able to add your own software, and being able to collaborate with others. So these are the features that I think are unique to this system that I'm going to talk about next in the next couple of slides. The first bit is how you add software. And this is something that a few of you have already seen or used with Conda environments. So the four types of Python that I've been talking about so far have been installed to everyone system-wide. But there may be software that you need that's not installed. So for example, in any of those, in none of those environments, I think we don't have a solar system integration tool called OpenORB that we quite frequently use for solar system work. So let's say I have a need to go ahead and install the OpenORB package. If the software that we want to install, exists in Anaconda, or specifically in CondaForge, then that becomes very easy to do. You have to open a terminal and then simply type these set of commands. So conda create -n name of your environment, and then the packages that you want to install there. And basically that gives you access to those packages. I'm going to go and demonstrate this now. You can follow along, and I'll copy and paste the lines that I'm going to use into Slack, so you can just do that as well. There we go. Just to demonstrate that this works and how it works. If you've used Anaconda, this will be familiar to you. If you haven't, unfortunately, we don't have time to go through a full tutorial of Anaconda, but there are numerous tutorials online on how to use Conda to create environments. If you're used to Python's virtual env, you can actually use that as well. But Conda is an equivalent of Python's virtual env that's a bit more general and more polished. So I'm going to go ahead and do this. Say conda create -n solar system OpenORB. James, there's a question.
Hey, I was just wondering, with the Conda environments, you say there's these default ones on. Is there any chance of me accidentally messing those up a bit by Conda installing something into those? Should I always make a new environment?
You won't be able to install it in the default ones. We will make sure that permissions are protected. Yeah. It'll tell you, you don't have permission to something along those lines. That's why you always need to create a new environment for yourself.
Okay, cool. Thanks.
So Mario, along those lines, can I pip install directly from the notebook?
Yes, you can. But again, you're going to have to create, at first you'll want to create a conda. No, you will be. Yes, you will be able, because pip install will install in your user directory if when it detects that it doesn't have access to the system-wide directories.
Good, thank you.
I prefer Conda a little bit more because you'll see in a second why. With Conda, a number of things are just happen automatically. Let's all try to run this and install environments and install this OpenORB package. So this takes a couple of minutes just to download and extract everything. Conda is great in many things, but speed is not one of its features. And so what this will do is this will set up OpenORB in an environment called Solar System in my home directory. That's writable by me, that's usable by me, and that you'll see soon. I can now run Jupyter notebooks from that environment as well. The other thing to mention here is everything that I do here, everything is written into my home directory. If I log out, if I close my browser window, if I come back tomorrow, it'll await for me there. Another thing to mention while we're waiting, all the home directories are backed up regularly. So we make backups daily, and we keep 30 days worth of backups. So if anything goes wrong, we're able to restore things. If you lose a critical file, you can ask one of our you can just ask on the LINCC channel one of our support helpers, and we'll try to go and get it for you. So there are some safety built-ins. In addition, as James asked, the system is set up so that you shouldn't be able to overwrite anything that would cause interference with other folks in the system. So you're only able to cause problems for yourself and your collaboration. I'll show you that in a second. But even there, we guard against it. Okay, so this got installed. Now I'm going to activate that environment, conda activate solar system. If you're more used to virtual envs, this is analogous to activating a virtual env in Python. And let me just demonstrate that OpenOrb is there. So if I type orb, I get a response saying, well, basically asking me to tell it what to do. So you can make any number of virtual environments, install any software in them. That's great. But the real advantage of this system with conda environments is if I go back now here, and if I hit new, notice how there are these 4 kernels. So that means I cannot yet use my let's say PyOrb, the Python version of OpenOrb that's in there. But any conda environment that has one more package installed, and it's called IPyKernel. Let me paste that as well. Okay. Do you want me to maximize this to make the fonts larger or make the whole window? Let's see, let me do that.
Maybe just the window larger or zoom in.
Is this better?
Yeah.
Okay. So if you type conda install IPyKernel or mamba install IPyKernel, I'll tell you a bit in a second what mamba is in that environment. So after you've typed conda activate solar system, what this will do is it'll basically install the bits and pieces that are needed for Jupyter to recognize this as a Jupyter environment. And while we're waiting for this to go through, what Mamba is, it's remember how I mentioned that conda is not very fast? Well, Mamba is a reimplementation of conda in C++ that actually speeds it up significantly. So here we go. You can just use conda if you're used to using conda, but you might wait a little bit more. So what this will do now is it'll install Jupyter Python kernels. It's extracting all the necessary packages. And this step just tends to take a while because Python applications usually come with hundreds to thousands of little files that have to be extracted and permissions set up correctly, etc. So it's just fundamentally slower than what one might hope for. And we're one step away from it being ready. And there we go. So what happened now? What happened now is once I have this IPyKernel package installed, if I go back to my Jupyter and if I refresh the page, click here under new, there's going to be now a new kernel called .conda/solar system. All the personal kernels all the personal environments that you set up will start with .conda, and then -solar system will be the name of the environment. So I can go ahead and click on that. And if I say import PyOrb, I have PyOrb. So this is now installed. It's an environment. I can use it from Jupyter. I can start adding things to that environment, it just works. So this is probably the easiest way to add environments, to add new software, like software that you really need to the setup on the hub. While you're in this environment, you can now actually pip install things as well. Pip install, give it a name of the package. I'm not going to do that just in the interest of time, but also please try to find a Conda package first, because Conda tends to work slightly better, and it's slightly more careful about what it writes to and what it doesn't. Pip can sometimes clash with Conda in the same environment, but if there's only a pip version of the package, feel free to go ahead and use that. If anything goes wrong, you can always create a new environment from the beginning. And again, it's yours. You don't have to worry about interacting with anyone else on the system. So that's the first thing I wanted to show you with environments. This note here that environments are only accessible to you is important. So if you install one of these environments, like if you have something that you have to use credentials and passwords and things like that, they'll only be visible to you. But the downside of this is that you cannot share them. You cannot give the link to someone else and say, hey, please use my environment. Now, that is a very useful facility. That ability for you to set up an environment, or maybe if there's a group that's collaborating, have a few people that are maintaining all the software in that group and then others using it. So we have built something to enable that as well. I think this will be especially useful to science collaborations. So this is where I'll tell you a little bit about that link folder that you've seen in your home directories. So let me go back to my directory here. See the folder named link, and zoom in. When you go into link, you'll see 3 subfolders: data, groups, and share. So what data is, data contains some shared centrally managed data. And here you see just one file. This is one baseline cadence from 2018 that we dropped there for one of the solar system sprints more than a year ago. That's the only thing that's there right now. But this is where we're going to be putting data that are available to everyone on the hub that are just broadly useful. There's a then directory called groups that contains group-owned, group-managed files. And I'll talk about that in just a second. This is the one that we're going to focus on, that one that's, I think, useful to everyone. And then there's a folder called shared. And this is one where anyone can write to, anyone on the entire system can write to, and anyone can read the data in that folder. So if you click on it, you'll already see a number of things, mostly by folks from the Solar System Science Collaboration. For example, one of my colleagues, like John Carrico, created a directory named John Carrico here, dropped some files in there, working on a tool called Atom, and now I can access them. I can try to execute these notebooks. I can try to run the code or access shared files, etc. So this is a way how to send things around, how to share data with the entire hub. That is something that you may want to do, but sometimes you may want to just limit sharing to your group, maybe to your collaboration or to any group of people you're collaborating with. And to enable that, one of the things we set up that's fairly unique is we basically, this JupyterHub basically takes all the organizations that you're a member of on GitHub and replicates those as groups on JupyterHub. So this is why when we were logging in, this is why I pointed out that you should go ahead and grant some permissions to the groups that you want to be collaborating with when you were logging in, when you were authorizing GitHub for the first time. So when you log in, any organization that you're a member of on GitHub is given on our system a Unix group in JupyterHub. I'll show you in a second what that means. And then a directory in LINCC/groups that is readable and writable only by members of that group. So remember that shared directory that I just showed you, visible by everyone. I just pointed out, I entered in have seen a whole bunch of files by people. These directories are readable and writable only by those who are members of those groups. So if I go to groups, this is my list. So this is the list of groups that I'm a member of. If you go to your group's directory, you'll see a different list there. But these are basically GitHub organizations. And the nice thing about this is if you need to add someone to the group and make it possible for them to browse files in this directory, all you need to do is you need to add them to your GitHub organization, and they'll show up on the system. So this is a nice way to enable distributed collaborations of large teams. So what's in these directories by default? They start empty. There's only this ends directory, which I'll tell you about in a second. But you can go ahead now and create files, create Python, Jupyter notebooks, do anything you ordinarily would in those directories. And anyone who's a member of the group should be able to go to this directory and see your files there as well, and even open them. So as I mentioned, it works with GitHub organizations. It's fully automatic. It basically, the idea is to enable quite seamless collaboration with this kind of system. So let's say the TVS collaboration can use the LSST TVS SC group to create directories for shared file that are supposed to be visible just to TVS, maintain software stacks, do anything that's needed for TVS work. That won't interfere with anyone else on the system, or it won't be even visible to anyone else on the system. So you're able to do private work there. And again, this doesn't have to be science collaboration. Any organization you have on GitHub, let's say you and like 3 or 4 colleagues want to work jointly on a project, and you want to keep those data private or in a location where only the 3 or 4 of you can write. Create an organization on GitHub. It'll get replicated into this environment, and you'll be able to use it.
Mario, you mentioned data. So is there a limit to how much data we should put there?
There's right now there's the total shared space is about a terabyte, but we can easily update. We can easily increase that as the needs grow. So if you want to upload something that's larger than a few tens of gigabytes or hundreds of gigabytes, let me know, and we'll work to find a place for it. Okay. Now I think
Maybe there is a question on Slack. What is the name of the package to import to test the solar system environment?
I am typing. It's PyOrg. So if you type import PyOrg, it should do it with 2 O's.
2 O's.
Yes.
Yeah, I wasn't able to do that.
PyOpenOrg. Yes. OOrg. So John points out in the Slack that each collaboration has their own GitHub organization, but not all collaboration members are actually members of GitHub organizations. And if you want to become a member of your collaboration's GitHub organization, you just contact your chair, and they'll get you on, and they'll send you an invite. Now, I think this already will be quite useful, but there's a potential problem here in that everyone who's a member of this group is able to both read and write files. So potentially it means if you have a very large group, of 150 people, if everyone's able to read and write files, somebody is eventually going to make a mistake. In our groups, it's usually me, because I tend to be not very careful, and I'll go ahead and type pip install in places where I'm not supposed to. So that's not ideal if you have a large group and if you have curated software that you want to make sure just works for the entire group. So we've built a system to make it possible to avoid those kinds of mistakes, or for those kinds of mistakes not to affect the system. So a frequent use for shared directories is to install and maintain common software environments. So like I showed you in the previous example, I installed a Conda environment just for myself. But what you'd ideally like to do is you'd like to install an environment for the entire group to use, and then have a couple of people manage that environment. The entire group should be able to use it, but not go ahead and delete it by accident. And so it's good to protect those environments from accidental corruption or deletion, because it's super easy to run pip install some package and then ruin upgrade everything in what's meant to be like an older version of an environment, especially true for large collaborations, as I mentioned. And so to defend against this, we've added a concept of admin accounts for each group. So if you have a group, let's say in my case, I'm a member of the group DiRAC Institute, member of the DiRAC Institute organization. There's an admin account called DiRAC Institute that if I log in as admin, if I log in as that account, and if I install software as that account, that software is going to be visible to everyone in that group, but they will not be able to delete it or change it. So this is kind of a way for a subset of people in the group to actually go ahead and install software, and yet at the same time to have that software be visible to everyone in the group, but not possible to delete. So I'm going to go ahead and demo how that's done. The important bit is who can do this. Who is an admin of a group? Right now, the way we've set that up is that those are GitHub organization owners. So if you're an owner of that GitHub organization, it means you can become an admin of that group on GitHub. And we'll add more features to this to be possible to specify exactly who needs to be admin, because not all people who maintain software are owners of organizations. But for the beginning, for a start, this is what we have. So let me. I think this part, if you know that you are an owner of an organization, you can try to follow along. But otherwise, you can just look at what I'm doing here. So I'm going to go and create a shared environment in my DiRAC Institute organization. So the first thing I'm going to do is I'm going to become the administrator for DiRAC Institute. So I'll use sudo-u DiRAC Institute-s. What this does is it basically logs me in as a new user called DiRAC Institute. And you notice that now it says DiRAC Institute here and not Juric. So I'm going to go and repeat our experiment with creating a new environment called with OpenOrg. Now I'm going to call this. Let me call that environment DiRAC, and I'll install OpenOrg into it. So now it should this installation should actually be a little bit faster, because now the system knows about OpenOrg and it's already pre-downloaded a number of packages from last time. Okay, almost there. And I'm going to go ahead and install the IPy kernel environment as well. IPyKernel package. And note that everything I'm doing as this administrator user for the group. So if you're an owner of a group, you can do that for your own group as well. And you don't have to contact any one of us. It's all set up so that groups can self-manage their software if they want to. So I go ahead and install IPyKernel. This will make it possible to use this in Jupyter. And I type exit so that I stop being the DiRAC Institute user. So now 2 things have happened. One, if I look at what are the Conda environments available to me as mjuric, type Conda end list to get a full list. And note, this is the solar system environment that I created for myself. And note now that this one appeared called DiRAC. That's the environment that my DiRAC administrator just installed. And anyone who's in the DiRAC Institute organization, so any one of my colleagues here at UW in DiRAC will now see that environment and be able to use it. So just to demonstrate, contact the DiRAC org, it's there. And the other thing that's happened because I installed IPyKernel, let me go back to something here. If I click new, you'll notice that there's now yet another kernel that showed up called DiRAC Institute DiRAC. So this is again a combination of the group name and then dash name of the environment. That's how it automatically encodes the name. I can click on this. I can start a new notebook. Let's demonstrate that PyOrg is actually there. Now let's demonstrate that it's the right one. So see, it's in DiRAC Institute, ENS, DiRAC, et cetera, et cetera, et cetera. And I have now I have that environment set up with the code, or I'm able to use that environment basically. So this is how the hub functions. It basically looks at all the organizations that you're a member of. It looks at all the environments that are defined in those organizations and puts them up here. So if you're a member of TVS, and if TVS starts curating a software environment for TVS purposes, you'll automatically see it here. If you're a member of both TVS, Milky Way, and Solar System, well, first of all, good luck doing all that work. Second, you're going to see all those environments just merged and shown when you click new here, and you'll be able to go ahead and access them. And this is a way to enable many groups to be on the same system and work together without necessarily cluttering this with a ton of things that you're not interested in. So for example, if you're a member of TVS and you're not a member of LSST Science Collaboration, you're not going to see the solar system kernels. So you're not going to have to wade through potentially dozens of things that you're not interested in here. So this is, I think, a feature that's going to become quite useful when we use it, and this is the kind of thing that's been requested over and over, and will hopefully be useful to you. Oh, and then just to demonstrate that bit that I mentioned about safety. So let me go here. So I am myself, I'm Juric. If I go to link, groups, DiRAC Institute, this here, the actual data files for the environments are in this ENS directory. Let's say I make a mistake and try to delete it. I won't be able to. Right? So this is something that we really wanted to make sure happen. Only the administrator of the group is able to change that software. So you can make sure that so it allows you to make sure that by accident you don't change something that you don't want. Lots of safeguards have been built into the system for that reason. All right. So that's what I wanted to show you about this. Try it out, see how it works for you, and I hope that this will spawn a whole cottage industry of maintained custom software stacks that can then be shared within groups and maybe made available throughout the entire system. So things to remember here and some best practices. Your home directory is visible only to you. So keep any private files you have there. By default, it's completely private, it's locked down. The group directory is visible only to anyone who's in the eponymous GitHub organization. Keep files that are supposed to be seen by your groups, keep common files there. And then there's that shared directory that's visible, which means both readable and writable to everyone. So place files there that you want to share with the entire hub. That's kind of the hierarchy of options. We're getting close to the end. I have only two more things I want to quickly show you. This now gets into the sort of grab bag category. One thing that I skipped at the beginning was that big orange button. I just said press start. Don't look at anything else when it asks you for server options. Those options have to do with resources. So what's available on GitHub on this JupyterHub. So let me go back. Let me shut down my Jupyter. I'll close everything, and I'll go to Control Panel, stop my server. This takes a second. So this will take me back. This will eventually take me back to this page. That's what I'm trying to emulate. There we go. Start my server. So by default, you get a server with 2 CPU cores and 8 GB of RAM. And for most work, especially with math, that's sufficient. But if you need more CPUs, this is because I made everything large. There we go. If you need more CPUs, more memory, more GPU, you can click on this link, and that'll expand a selector for you to pick some of those machines. Right now, we have a selection of 5 machines. We have 4 that kind of different number of CPUs and amount of memory, and then we have the 5th one that has GPUs as well. So one NVIDIA T4 GPU, if you need to do something that's GPU related. You can simply click on one of these, hit start, and then wait for the server to spin up. If you're unsure what to use the default one. Always use the smallest one. The price is listed here. This is not the price that you pay. This is the price that we pay. But kind of help us keep the cost down, but not running, say 128 gig machine if all you need is a couple of gigabytes of memory. Federica, you have a question?
Maybe. Do we get warning that we're using a GPU environment without using a GPU, kind of like Collab does? I find that useful, but it might be complicated.
Not right now. That's a good idea. That's something we could add. You will get when you're logged in. You will at the top of Jupyter. There's going to be there's a little kind of bar that shows you how much memory you have in the machine. So that kind of gives you a sense for which one you're using. I recommend you to use the default ones. The way those are set up, actually logging into those is quicker. If you try to use one of these, it'll take between 4 and 5 minutes to actually get it started, because it has to go out to Amazon, find a machine, and prepare it, and so on. We have a couple of these that are always running that will quickly log you in. So that's another incentive to just use the default type. So that's one thing I wanted to point out. If there's something that you find here, if there's a different machine type that you need, different combination memory CPU, talk to us. We are able to add more of them. Right now, this is just a small selection of what Amazon has to offer. And the last thing I want to show you is there's a desktop environment. If you click on New, you'll notice that just below Terminal, there's an entry for Desktop. And I go to New and click Desktop, what you're going to get is, first time you do this, it'll type something went wrong, connection is closed. This is a known bug that we're working on fixing, but then just hit refresh. And what's going to happen is it's booting up, so give it a couple of seconds. But what's going to happen is you're going to be greeted by a full-blown GNOME desktop that runs within your Jupyter environment. So here are all your directories. But other than that, this is full-blown graphical Linux desktop that runs in a browser. So you can spin up DS9 if you want to quickly take a look at a FITS file that you have uploaded there. You can even, I don't recommend this, you can even spin up a browser. I think we have Firefox installed. This will not be very pleasant to use. It's a remote graphical desktop. It takes a while for data to be shifted back and forth, but in a pinch, if you need it, it comes in quite handy. So I just wanted to show you that to give you a sense for, or so you're aware of that it's available if you need it. Okay, and that concludes what I wanted to show you about what we have available in the hub. Last bit is just something about support and development. Let's use LINCC on LSSTC Slack as our main communication channel. So just feel free to join there and give us comments, give us questions, give us feature requests, tell us what works, tell us what doesn't. We're eager to hear and to help out. We have our support team listening in there as well. So if you ask a question, it's more likely than not then that the first people you're going to hear from are one of Aditi, Aiden, or Paulo, and then our devs and researchers, so Stephen and Colin, who have set up most of this on the back end, and myself are there as well. And in 2022, you'll see that this is all right now, this started as a research project, and this is something that we've been doing in our free time, to be honest. And now with LINCC starting, we're going to be getting a larger, more professional software development team coming in 2022. If you're one of the folks who are interested in building things like this, and or have a software engineer friend who might be interested, follow us on LinkedIn to be notified when those job openings go out. So with that, I'll flip to the next slide with future plans. I mentioned SSH access. We'll have websites, we'll have more precursor data sets, we'll have automated installations of weekly stack releases. Right now we do them by hand. Lots of other things, and I hope that in about a year from now, this will culminate with collaborative editing. We want to make it possible, like you would do in Google Colab, to have more than one person work on the same notebook at the same time. That is just fantastic for collaboration, and that's kind of where all of this is going slowly but surely. Okay. I'll stop that. This finishes this whirlwind tour of the hub. Thank you very much. We're looking forward to using this in both ways we've imagined and ways we didn't. Please let us know how well it works, and we're here to help out and make this a useful resource for getting started with LSST Science. Thank you.